All right, so we're going to look at section 2 of chapter 5, applying Newton's laws. So we learned the three laws of Newton in the last video. We said Newton's first law was that any object in motion stays at motion, any object at rest stays at rest, and that's called the law of inertia. Newton's second law says that the force on an object is equal to its mass times its acceleration. So in this particular section, we'll be applying those laws and using vector diagrams, or we call them free body diagrams, in finding the net force and the mass, acceleration, and different things like that. So a free body diagram, again, these are vectors, so it's always really important with a vector to draw out a sketch or to draw what we call a free body diagram. And this is just a diagram that shows all the forces acting on the object. So to simplify, to simply a real life situation, a free body diagram is the object often represented as a point. So you have a point, and then you have, all right, so that force is acting upward. So the astronaut's pushing up. That means that force is going to be acting upward. This astronaut is pushing to the positive x direction. So that means that his force is acting in that direction. And that's a free body diagram. Okay. And we represent that object, whatever it is, instead of drawing out the actual object, we just represent the object as a point. All right, to use a free body diagram in the solution of problem solving involving Newton's second law, we have to do the following things. So these are our kind of our steps. Once all the forces are drawn on the free body diagram, a coordinate system is chosen, and each force is resolved in its components. So remember, the force is a vector, so we can take any vector and we can resolve it or break it up into its two component parts. And that's what you'll be doing with each of these forces. At this point, so we get them divided into their components, we can apply Newton's second law to each coordinate direction separately or to each force separately. So step number 1, draw that free body diagram. Know where your forces are going. Step number 2, take those forces and resolve them into their components, the x direction and the y direction. So you'll have an f of x and you'll have an f of y. Once you get those two, you then simply use Newton's second law, force equals mass times acceleration, to find the force for those two components. Okay? All right, so we're going to look at an example that illustrates how we're going to do this. And we're talking about the same two astronauts you saw in the figure previously, those two astronauts pushing on a satellite. So here they are again. Here's your two astronauts. Astronaut Y is pushing up, so that's going to be F2, pushing up. F1 is pushing to the right, so F2 is going to be our force in our Y direction. F1 will be our force in our X direction. Okay, so the problem tells us that this astronaut is pushing with a force of 46 newtons. Okay, now because it's going directly in the x direction, we don't, our two components, we break up each one into its components. It's x direction, it's y direction. Well, since it's going in the x direction, it has no y direction, so F1y. So the y component of the F1 force is 0. And then our second astronaut is pushing up, and all he's doing is pushing up, but he's pushing up with 46 newtons of force as well. So F2, there is no x direction for F2 because he's not pushing to the left or right. He's only pushing up. But he does have a y component of F2, which is 46 newtons. So then what we're going to do is we're going to take F equals ma for the sum of all of your x components, and we're going to do F equals ma for the sum of all of your y components and add those together. Okay, so we're going to take, here's our x components. So 46 plus 0. Here is our y components. So that's going to be 0 plus 46. 46 newtons equals mass times acceleration in the x direction. 46 equals mass times acceleration in the y direction. So then we're just going to solve for a of x and a of y. 0.049, 0.049 each time. Now, these are our components. So remember from the previous chapter that we can find our resultant from the components by using Pythagorean theorem. Okay, and then you can find the angle by using second function tangent of the y component over the x component. That's a negative one. There we go. All right, so the resultant is going to have a magnitude of 0.069. And if we do second function tan of 1, that is 45 degrees. So it's going to be acting at a 45-degree angle. His acceleration will be acting at a 45-degree angle. So that means this whole thing is going to move upward in a 45-degree angle. All right. So there are several types of forces that we can encounter in everyday situations. We can encounter what's called the normal force, and normal forces are the forces that are perpendicular. I'll make sure I say this correctly. I want to say they're perpendicular to the surface. That's correct. They're perpendicular to the surface on which that object is resting. And then we have forces due to gravity, and then we have forces due to stretch or compression of springs. So if we're pulling on a spring, or that a spring scale like we saw in some of those other diagrams, that's a spring being pulled or compressed, depending on whether you're attaching a weight to it or removing the weight from it. So those are our forces that we encounter in everyday circumstances. So here's some diagrams of what those look like. So this would be a normal force. Say normal force is always acting perpendicular to the surface. Okay. It's the object due to weight. The force due to weight is acting directly down on that surface, but the normal force is acting up again because forces occur in pairs, and they occur in equal and opposite directions. So the upward force, which is perpendicular to the surface, is the normal force. The force exerted perpendicular to the surface between any two contacts, that's what we always call the normal force. Weight. Weight of an object is the force of gravity on that object. And so again, it's always going to act downward. So an object's mass in free fall, an object of mass m in free fall has only one force acting on it, and that's its force due to weight. Okay. And the acceleration of that force due to weight is the acceleration due to gravity. So sometimes we can say force is equal to mass times acceleration. We can also say that an object's weight, W, is equal to its mass times acceleration due to gravity. So the weight of an object is equal to its mass times the acceleration due to gravity, where capital W is our weight. And it's a little confusing. I would prefer you use FW because capital W looks a whole lot like work. So force due to weight of an object should really be abbreviated FW, force due to weight. And that's equal to mass times acceleration due to gravity. All right, weight and mass, remember, are not the same thing. We've talked about this earlier, but just to reiterate, weight is the gravitational force. Mass is a measure of an object's inertia. It's a measure of the amount of matter that an object has, and it makes no difference its the location. And that's the big difference between weight and mass. Weight is a force, It's the gravitational force on an object, whereas mass is just the amount of matter that that object is made up of, no matter whether you're on the Earth or whether you're on the moon or whether you're on Jupiter, doesn't matter. But for weight, those things matter because gravity is different in each of those locations. Okay. So as a result, the weight of an 81 kilogram person is 795 newtons on Earth, but only 131 newtons on the moon, because the gravitational force on the moon is less than the gravitational force on the Earth. So weight can change in an accelerating system. So if you've ever been in an elevator or been, it's not just an elevator, but that's just a good example, where your acceleration may speed up really, really fast. That means that that your quote unquote your weight will change. It's not your mass doesn't change, obviously, but because your acceleration is changing, your mass is holding constant, but your acceleration is changing. That means that force due to weight can also change. Um, so you get that sensation of weightlessness, or you get that little weird feeling in your stomach. Um, that's that sensation due to the fact that um, you have a different weight due to your accelerating environment. So, like when you get on and off an elevator, you first start that elevator, or when it stops, you get that little ooh feeling in your belly. That's because you have a sensation of your weight being different than what it was, because your acceleration is changing. Also, this is what happens when we model free fall, or when an object is in free fall, or when we model weightlessness or try to get to that weightlessness of space. And they do that by basically going up in an airplane and then letting the airplane drop really fast. Um, and so when that happens, you get that your apparent weight is zero, so you go weightless. Um, and they do that to get prepared for space because that is a weightless environment. So, if you're in a system that has a downward acceleration of g, then your apparent weight is zero. So, in free fall, in a freely falling elevator or a spaceship, or in this case, an airplane that just starts to drop really, really fast and then is modeling free fall, you get that feeling of weightlessness. So it happens, experience weightlessness in an airplane flying along a parabolic path. So they go up, they climb up, and then they drop back down, and then they climb up, and then they drop back down, and that causes that weightlessness. Okay, springs. So it's another a force that we encounter in our everyday life is the force of a spring. They exert a force when they are either stretched or compressed because they're going to want to come back to their original equilibrium position. So here it is. Here's the equilibrium position with no weight or anything attached to it. We attach a weight to it, and it causes that spring to stretch out. And the more weight we add, the more that spring stretches out. When we remove that weight, the spring will compress back to its original equilibrium position. So we can see that. So here's its equilibrium length. So this is when x is equal to 0, just its normal length. If we attach a weight to it, it's going to cause that weight to stretch, which means that we will have a distance x. It stretches by a certain amount x, again, depending on the weight. So the force that's applied is going to be equal to some constant k times x, the distance that that thing's stretched. And that will be the force that's applied to that spring. All right, so When the spring is relaxed, you don't have any change in length, so x is 0. When the spring is stretched, you have a length equal to x. And so we get what's called Hooke's law, and that is that equation you saw on the previous page, that the force of that's on that spring is equal to a equilibrium constant k times x, which is the distance that spring stretches. All right, so there's Hooke's law. Pay attention to the units. K is in newtons per meter. So X is in meters, force is in newtons, which means K has to be newtons per meter. The larger the spring constant, the greater the force exerted by the spring. A large spring constant corresponds to a really stiff, hard to stretch out spring. All right, objects with zero acceleration are said to be in equilibrium. According to Newton's second law, the net force must equal 0 if an object is not accelerating. So an object in equilibrium does not have any net force acting on it. So our little graphic got mixed up. But so the sum of the forces has to be equal to 0. An object in equilibrium may be either at rest or moving with a constant velocity. So remember, if it's moving with a constant velocity, its acceleration is 0. So it doesn't have to be just sitting still. It could be moving with a constant velocity, which would make acceleration 0. The force that opposes, okay, so this is section 3, so we're going to stop here for today. We will start looking at friction in section 3 tomorrow. Hope you have a great day.